Good day, students. In this clip, we're going to be going over 4 examples using the rules of definite integrals. Before we do that, we're going to take a look at the rules for definite integrals first, okay? So for each rule, I'm going to be showing you a derivation of each rule using FTC Part 1, the Fundamental Theorem of Calculus Part 1, okay? So let's write that down first. So FTC Part 1 is as follows. It states that the definite integral from a to b of a function f of x dx is equal to the antiderivative of f evaluated at the upper limit of integration minus the antiderivative of f written as uppercase F evaluated at the lower limit of integration. Okay, so this is FTC part 1. This is what we're going to be using to show that our rules are in fact correct. Okay. All right, let's take a look at the first rule. Okay, the first rule is order of integration. Okay, rule number 1. Order of integration. All right, so the order of integration rule is as follows. It states that the definite integral from a to b of f of x dx is equal to negative of the definite integral of b to a of f of x dx. Okay, so what this rule is telling us is that if you switch the order of integration to preserve equality, you must introduce a negative sign in front of the integral expression. All right? All right, let's prove that this is correct using FTC part 1. Okay, we're just going to do a short proof right here. So proof. So we're going to start from the left side. We have the definite integral from a to b of f of x dx. Okay, so applying FTC part 1, this can be written as the antiderivative of f evaluated at the upper limit minus the antiderivative of f evaluated at the lower limit. Now what if we switch these two terms around? This becomes negative f of a plus uppercase f of b, or the antiderivative at b of f at b. Now, what happens if we factor out a negative from these two antiderivatives? This becomes negative bracket antiderivative of f at a minus antiderivative of f at b. Now, I can apply FTC part 1 to this quantity inside the bracket, okay? So it becomes negative of the definite integral from b to a of f of x dx. Okay, so that shows that this rule is in fact accurate. Now let's switch our attention to the second rule, which is known as the zero rule. Okay, zero rule. Now what does that one say? Well, it says that the definite integral from a to a of f of x dx equals 0. One way to easily see that this rule is correct or accurate is think of it as area, using the area definition of an integral. Okay, if this is an area, this would be the height of f of x, and the width will be 0 because you're going from a to a. So what is the area of a rectangle or region with 0 width? The area is 0. Okay, so there you go. Now let's prove that this is correct using FTC part 1. Let's do a real quick short proof here. Starting from the left side, the definite integral from a to a of f of x dx. If I apply FTC part 1, I'm going to have the antiderivative of f evaluated at a minus the antiderivative of f evaluated at a. All right, subtracting two identical terms, final answer is going to be 0. So we see that this rule is in fact accurate. Okay, let's take a look at the third rule. The third rule is the constant multiple rule. Very similar to that of the derivatives, constant multiple rule. All right, so what is the constant multiple rule? Well, there are two of them. First one, part A, says that the definite integral from a to b of a constant k multiplied by a function f of x dx is equal to the constant k times the definite integral from a to b of f of x dx. Okay, so what this rule is basically telling us is that if you have a constant that can be factored out of a function that you're integrating, that constant can be factored out of the integral expression. All right, and then when you're done evaluating the integral, you just multiply a constant by that value. Now let's prove that this is correct using FTC part 1 proof. Let's start from the left side, the definite integral from a to b of k times f of x dx. If I apply FTC part 1 here, I'm going to have the constant k times the antiderivative of f evaluated at the upper limit minus the constant k times the antiderivative of f evaluated at the lower limit. What you see we can do here is that we can factor out these two k's, right? If we do that, we're going to have k multiplied by the antiderivative of f evaluated at the upper limit b minus the antiderivative of f evaluated at a. Okay? Now using the reverse of FTC part 1, we can rewrite the difference of these two antiderivatives as a definite integral. Okay? So let's write it down. This becomes k times the definite integral from a to b of f of x dx. So you can see that the constant multiple rule is in fact correct. Now let's look at the b part of the constant multiple rule. That's a special case of part A, in the case where k equals -1. So what if we have the definite integral from a to b of negative f of x dx? So the constant multiple rule says that this is equal to negative times the integral from a to b of f of x dx. Okay, you have to be careful here. This one is telling you that you can factor out the minus. You don't have to switch the order here. If you have a minus in here and you want to factor it out, that's perfectly fine. Okay? It's only when you switch the order of integration that you can introduce a negative to a function that did not have a negative before. But if there's a negative in the function, you can factor out the negative and preserve the order of integration. All right, now let's prove this. Let's prove this second case of the constant multiple rule. Proof using FTC part 1. The left side, the definite integral from a to b of negative f of x dx can be written as the negative, this negative, keep it, of the antiderivative of f evaluated at b minus negative times the antiderivative of f evaluated at a. Okay, now let's resolve the signs here. We have negative antiderivative of f at b plus antiderivative of f at a. Now let's factor out the minus from these two quantities, these two antiderivatives. So we're going to have minus bracket antiderivative of f at b minus antiderivative of f at a. Okay, now I can use the reverse of the FTC part 1 to express this as an integral, as a definite integral. So this will become negative of the definite integral from a to b of f of x dx. So we can see that this rule is in fact correct. All right, let's shift our attention to the next rule. This is rule number 4. Rule number 4, we're going to take a look at the additivity rule. Okay, additivity. So it's actually possible to add two integral expressions. Alright, so the additivity rule is as follows. It says that we have two definite integrals with a special kind of boundary. So let's say we have the integral from a to b of f of x dx plus the integral, a definite integral starting from the upper limit of the first integral b ending up at another value c. The additivity rule says that we can express this as the definite integral from a all the way to c of f of x dx. Okay, so this is the additivity rule of definite integrals. All right, let's prove this. So short proof using FTC part 1. All right, so using FTC part 1, let's write on the left side, definite integral from a to b of f of x dx plus the definite integral from b to c of f of x dx. This can be written as antiderivative of f evaluated at b minus antiderivative of f evaluated at a. That's for the first definite integral. Plus for the second one, antiderivative of f evaluated at c minus antiderivative of f evaluated at b. All right, let's see if we can simplify this. If you notice, the antiderivative of f at b cancels out. And I can switch the order of this expression right here. I can write this as antiderivative of f at c minus the antiderivative of f at a. Okay, now using FTC part 1, the reverse of it, I can write this as the definite integral from from a to c of f of x dx. So you can see that the additivity rule is in fact accurate. All right, let's take a look at the last rule I'm going to show you. There are two other ones that I'm not going to cover on this clip, the domination and max and min. You might also want to examine those later on, okay? So I'm just going to focus on these. The last one I want to show you is the sum and difference rule, okay? Well, what is the sum and difference rule for definite integrals? Well, it's as follows. It says that if you have the definite integral from a to b of the sum or difference of two functions f of x and g of x, this can be written as the definite integral of the respective functions that you're adding or subtracting. So the definite integral from a to b of f of x dx plus or minus the definite integral from a to b of g of x dx. Okay? So there goes the sum and difference rule for definite integrals. Well, let's do a short proof using FTC part 1 to show that this rule is in fact correct. Okay? So starting from the left side, we have the definite integral from a to b of f of x plus g of x dx. Now applying FTC part 1, we're going to have the antiderivative of f evaluated at b plus, so it's supposed to be plus or minus, plus or minus the antiderivative of g evaluated at b. So what we do is you find the antiderivative and plug in the upper limit first. So this entire thing minus the antiderivative of f evaluated at a plus or minus the antiderivative of g evaluated at a. Okay? All right, let's go ahead and simplify this. So we're going to have um, antiderivative of f at b plus or minus the antiderivative of g at b minus the antiderivative of f at a. Distribute this minus to this other term right here, minus plus or minus the antiderivative of g at a. Okay, let's reorder these antiderivatives. So we're going to have the antiderivative of f at b minus the antiderivative of f at a plus or minus the antiderivative of g at b minus plus or minus the antiderivative of g at a. Okay, so this first two we can group them together, and we can clearly see the applicability of FTC part 1. And the second one, we just have to factor out. You see this plus or minus here, this plus or minus in front of these two terms. We can factor them out. If we do that, we're going to have plus or minus bracket antiderivative of g at b minus antiderivative of g at a. Okay? Now, let's see. We can now apply FTC part 1 to these two quantities here. So for the first quantity, we'll have the definite integral from a to b of f of x dx plus or minus the definite integral from a to b of g of x dx. Okay, so that shows that the sum and difference rule for definite integrals is in fact correct. Now let's take a look at four examples applying these rules that we just covered here. All right, so examples. Instructions are as follows. Use the given definite integrals to find the value of the following. Okay? So the definite integrals that we are going to be using are as follows. We know we're given the fact that the definite integral from -3 to 1 of f of x dx equals 3. The definite integral from 5 to 1 of f of x dx equals 4. And the definite integral from 1 to 5 of g of x dx equals -6. Okay? All right, let's take a look at part A. Part A, we have to use this information to find the definite integral from 5 to 1 of f of x minus g of x dx. All right, so what property are what rule are we going to apply here? We're going to be using the sum and difference rule. To be specific, we're going to be using the difference rule, okay? So that tells us that if we have the definite integral of the sum or difference of two functions, we can reduce that into the definite integral of the respective functions that you're subtracting or adding, okay? So this can be written as the definite integral from 5 to 1 of the first function, f of x dx, minus the definite integral from 5 to 1 of the second function, g of x dx. All right, we can clearly see that the value of this definite integral is 4, but we have a problem here because the limit of integration does not match what we know. So since we have a mismatch, what can we do to make them the same? Well, we just simply apply another rule. What rule is that? We're going to apply the order of integration rule here. Okay, so this can be written as integral from 5 to 1 of f of x dx This is good, we don't want to bother it. Minus, now we're going to switch the order of this integration. Okay, we switch the order of integration, what happens? This, you must switch the sign, right? So this becomes a plus the definite integral from 1 to 5 of g of x dx. Okay, now we're good to substitute the values of each integral. So first one, integral from 5 to 1 of f of x dx is 4, plus the second one is negative 6. 4 plus negative 6 is negative 2. Alright, so there goes your first answer. Now let's take a look at the B part. For the B part, we're going to be looking for the definite integral from 5 to 1 of negative 4 times g of x dx. Okay? Now, let's see, how can we evaluate this definite integral right here? We have to get rid of this negative 4 somehow, because we know what the definite integral from 1 to 5 of g of x dx is. So we're going to apply the constant multiple rule first. So if we apply the constant multiple rule, that gives us the ability to factor out a constant that is being multiplied to a function. So we're going to have negative 4 times the definite integral from 5 to 1 of g of x dx. Now, does this match what we know? Absolutely not. The orders are reversed. So what we're going to do here is we have to apply the order of integration rule again to switch the order. So this becomes negative 4. Now when we switch the order, this minus becomes a plus, right? So plus the definite integral from 1 to 5 of g of x dx. Okay? Now, it's exactly how we want it. So we're going to now make a substitution. This becomes 4 times negative 6, which equals negative 24. All right, let's take a look at part C. Now, what if we are asked to find the definite integral from negative 3 to 5 of 1/5 of g of x dx? All right. Well, actually, it's not g of x. Let's do f of x. F of x dx. So if you look at the options we do not have any integral going from negative 3 straight up to 5. We have this one going from negative 3 to 1, and then this goes going from 5 to 1. So is there any way we can express this using a combination of these two? And the answer is absolutely. How do we do that? Well, we have to break it up. So what we're going to do here is we're going to make use of the additivity rule to break up this integral. All right. So since we know that 1 is in between these two, we can express this definite integral as the definite integral from negative 3 to 1 of 1/5 f of x dx. I should have factored out the 1/5, but I'll do it next. So we have that plus the definite integral from 1 to 5 of 1/5 f of x dx. Okay? Now you see how I applied the additivity rule here. Going from negative 3, stop at 1, and then from 1 to 5. Now let's see if we have a match. Oh, nice. This one some matches with this after I take out this 1/5. This one just needs a little bit of work. We just have to apply the order of integration rule to this one right here so that it matches this, and then we're good to go. All right? So let's go ahead and do that. This one, I need to apply the constant multiple rule, factor out 1/5, And then we have the integral from -3 to 1 of f of x dx. And then plus, I'm going to, if I apply the order of integration rule and the constant multiple rule simultaneously to the second definite integral, I'm going to have negative for switching the order, and then factoring out the 1/5 using the constant multiple rule. 1/5 times the integral from 5 to 1 of f of x dx. Now I'm good to make my substitution. Okay, so this is going to be equal 1/5 times the first one. Integral from -3 to 1 of f of x dx is 3, minus 1/5 times the definite integral from 5 to 1 of f of x dx is 4. Okay, so this can be written as 3 over 5 minus 4 over 5, and your final answer is -1/5. Alright, so that goes the value of part C. Okay, let's take a look at the last one, part D. So for this one, what is the definite integral from 5 to 1 of 2 f of x minus 7 g of x dx? Okay, all right. So first thing I'm going to do, I'm going to apply the sum and difference rule and the constant multiple rule simultaneously. So this can be written as 2 times the definite integral from 5 to 1 of f of x dx. Now, the g of x, I know the integral from 1 to 5, so we can also apply the order of integration rule here too. So instead of making this a minus, this will be plus. Applying the constant multiple rule, 7. And then the sum and difference rule enables me to find the integral of the second function, g of x, with the order reversed from 1 to 5. Okay? So let's go over, recap the rules I just used here. The difference rule enables me to integrate these individual functions that we subtracted. The constant multiple rule enables me to factor out the constants. The order of integration rule enables me to switch the order of integration for g of x so that it matches what we have, and then we can then evaluate its value. Okay? So now what does this become? This becomes 2 times, we know what the first integral is equal to 4, plus 7 times, we know what the second integral is. It is -6. And then when we simplify this, we get 8 minus 42. And our final answer is -34. Alright, -34 is the value of our definite integral. So that's that. So thanks so much for taking the time to watch this presentation. You can feel free to subscribe to my channel by clicking here. And please post a comment to let me know what you think. I really appreciate it. More clips can be found on mathgotserved.com/calculus. Thanks again for watching and have a wonderful day.